So for simplifying rational expressions, we're going to look at the review here. The first thing we're asked to do is find the domain for each rational expression. So just to refresh your memory on what domain means, concept-wise, essentially domain is all of the x values or all of the independent values, variable values that could work for the expression. So it could be x values, or in this case you see number 2 is an r. It doesn't change the way you find it. The idea is the domain is the list of all the numbers that can be plugged into the expression and give you a value. So the idea there is there are certain values potentially that if I plug them in, I would get something undefined. And the quickest way to find them when we're dealing with a rational expression is to look at the denominator. So whenever you see domain for a rational expression just means a fraction. Really what we're asking you to do is find the values that work by examining what's happening in the denominator. So what I mean by examining what's happening in the denominator is if you look at number 1, what I want to do is simplify the denominator first, in this case factor. And once I factor it, which x squared minus 1 factors into x plus 1, x minus 1, I want to find the value, set the denominator equal to 0, and find the x values for that equation. When I find the x values there, I'm essentially finding the values that don't work, which means the values that do will be everything else. Let me walk through the process and then kind of explain it again. So again, once I factor the bottom as much as possible, I can set each factor equal to 0 separately. So solving each one, I should get -1 and +1. So here's what I found. At x equals 1 and x equals -1, if I plug them into the original expression, I would get a number divided by 0. So those two numbers are what makes the bottom 0. And when the bottom of a fraction is 0, the whole value is undefined. So at those values, the expression is not defined, which means the domain should be all the other values. So the way we write that is by using a set of intervals. So if -1 doesn't work, that means everything before it works. So the way you write that is the interval from -infinity to -1, and then -1 itself doesn't work. So it's essentially like a break or a gap between my values. And then everything between -1 and 1 works, so we write that as a separate interval. And then 1 itself doesn't work, and then everything after 1 works. So if you look at the three intervals, -infinity to -1 just says all the x values less than -1 work. If you look at -1 to 1 as an interval, that's saying all the numbers between -1 and 1 work. And then if you look at the last interval, 1 to infinity, that's saying everything after 1 works. And so by finding the values that don't work, 1 and -1, we can write intervals for the rest, and that would be our domain. So that's the process for rational expression. First, factor or simplify the denominator, then set it equal to 0 and solve. So number 2, I'm going to do something similar. So I'm going to factor the denominator, which factors into r plus 8, r plus 1. Now that I have two factors, I want to figure out where the denominator is 0 by setting each factor equal to 0 separately. When I solve those, I should get r equals -8 and r equals -1. So at those two r values, the expression doesn't work, which means at all the other values, the expression works. So one way that might be helpful is if I kind of draw a number line and put my two numbers on there. And what I colored in orange basically represents everything before -8 works, everything between -8 and -1 works, and then everything after -1 works. So that's 3 pieces, so I'm going to have 3 intervals. So my domain is going to be -infinity to -8. Union, just saying more than one interval works for the domain. So then I'd have an interval from -8 to -1, and then I'd have an interval from -1 to infinity. So because I have 2 places where the domain, where the expression doesn't exist, I have 3 intervals to describe all the other values. Similar for number 3, I'm first going to factor the denominator as much as possible. And remember, for a rational expression, the domain is really just dealing with what makes the denominator 0, because that's where the whole expression doesn't work. It's not defined. So I factor the bottom. The only thing I can do is take out a greatest common factor. So now I can set each factor equal to 0, x and x plus 4. And x equals 0 is already solved, so there's an answer. And then to solve the other one, I should get x equals -4. So I have 2 x values that don't work, which means I should have if I put them on a number line, 3 intervals that do work for all my x values. So I'm going to describe them very similarly how I described them in the previous problem, which is negative infinity to negative 4, negative 4 to 0, and 0 to infinity. So those 3 intervals are with all the values that work. The easiest way to find them is by finding the values that don't work. So that's how you would approach the domain of a rational expression. The next few problems is just asking us to simplify. So if I just have a rational expression, here's kind of the base thing you should try and do. Simplify the top as much as possible, simplify the bottom as much as possible, and then see if anything reduces in the top and bottom. That's kind of the process there. If you look at number 4, the top z cubed doesn't simplify at all. I mean, I could write it z times z times z if I wanted to. And the bottom, 4 times z to the 5th, what I might want to do is just think of those as really a number times that expression. Because the top and bottom are really as simplified as necessary, all I'm going to look to do is reduce. So what I should notice is there are 3 z's in the top and 5 z's in the bottom. So the 3 z's on the top will reduce with 3 on the bottom, leaving 2 left over in the denominator. So what that leaves me is 1 in the top, not 0, because remember, when we reduce, we're really dividing. So we're dividing z to the 3rd by itself, it gives me 1, and taking z to the 5th and dividing it by z to the 3rd leaves me with 2 z's. So I should have 1 over 4z squared. Number 5 is still a rational expression, but you'll notice it looks slightly differently. What I'm going to do is factor the top and bottom as much as possible. The top, only a GCF will come out. So if I factor a 6 out, I should get 6 times the quantity x minus 5. And then the bottom, if it factors, will factor into 2 binomials. And what it factors into is x minus 5, x minus 2. So then, when I look to reduce, I look for a factor in the bottom that reduces with a factor in the top. And that entire binomial, x minus 5, reduces in the top and bottom, leaving me with just 6 in the top and just x minus 2 in the bottom. And that would be the simplified rational expression. Similarly, for number 6, I'm going to see if I can factor it. So the top, I can factor out a 6, so it becomes 6 times x minus 2, and then the bottom is actually a difference of 2 squares, so it'll factor into x minus 2x plus 2. And then looking if anything reduces in the top and bottom, I have a factor of x minus 2 in the top and 1 in the bottom, so those reduce, leaving you with just 6 over x plus 2. Now number 7, what you notice is slightly different. It's actually a rational expression times another rational expression. What I like to do for these problems is see if I can reduce first before I try and multiply across the top and across the bottom. You can multiply across the top and get 70x, and multiply across the bottom and get 5x cubed, but then you'd be reducing 70 and 5, which is fine, but it's probably easier to reduce first. What I mean by that is, what I notice is I have a 5 in the denominator and a 10 in the numerator. It's really 2 fractions multiplied together. So they don't have to be across from each other. One just has to be in the bottom and one has to be in the top. So this 5 will reduce with this 10, making it 2 and 1. So divide them both by 5. And then I have 1x in the top and 3 x's in the bottom. So one of the x's in the top will reduce with one of them in the bottom, leaving 2, or x squared, in the denominator. Now once I've reduced everything, now I simply just multiply across the top and across the bottom. So across the top I have 7 times 2, which is 14. And across the bottom I have 1 times x squared, which is just x squared. And that would be as simplified as possible. Number 8, I have a trinomial over a trinomial. The first thing I would like to try and do is factor, but first notice the top and bottom can both have a greatest common factor taken out. So if I do that, factor 5 out, I get w squared plus w minus 6. And in the denominator, if I factor out a 7, I would get 7 times w squared plus w minus 6. And if at this point you're paying attention, what you might notice is the 5 and the 7 out front, what I have left inside the parentheses is actually the same in the top and the bottom. Now you might want to look at that and say, oh, does w squared plus w minus 6 factor? It does, and the bottom one also factors, but if you factored the top and bottom, you'd end up with the same factors in the top and bottom. So the easiest thing to do is right here, notice that w squared plus w minus 6, I have one of those in the top and one of those in the bottom, so I would just reduce those as is, leaving you with just 5 over 7, and that would be your answer. And then number 9, the difference between number 9 and number 7 is I have a rational expression divided by a rational expression rather than multiplied. So the first thing we like to do in these problems is turn it into a multiplication problem. So keep the first fraction as is, 2g over g plus 3. But instead of dividing by that fraction, it'd be the same as multiplying by its reciprocal. So what you'll notice is, to change that division to multiplication, I had to flip that second fraction over. And now I have a fraction times a fraction, looking to see if anything reduces before I multiply. So what I notice is, I have a g plus 3 and a g plus 3, one in the bottom, one in the top. And also be careful, one thing we have a tendency to do is we see g's in the top and bottom and we try and cancel them. But be careful, each part of each fraction is its own quantity. So like 2g is together, g plus 3 together, g plus 3 in the top on the right, and g plus 8. You can't cancel the g's and just leave the numbers. I like to think of them as binomials that are connected. So I have the entire binomial g plus 3 that reduces, and in the top and bottom, leaving you just 2g in the top and g plus 8 in the bottom. That would be your answer. You don't need the parentheses on those anymore once you've reduced them, but if you had them, it would be the same answer. For number 10, we are going to factor each part as much as possible and then see if and what reduces. So the 6 minus 18x and the 2 minus 6x, and those two fractions are both binomials that share a greatest common factor. So if I factor 6 out of the first one, I would get 1 minus 3x. So I have 6 times that over 4x squared times, and then the x cubed stays x cubed, but the bottom, if I factor out a 2, I get 1 minus 3x as well. And right here, before I multiply them out, I'm going to reduce. So I see the 1 minus 3x in the top and bottom. That would completely reduce. Then I'm looking for anything else that reduces. And what I notice is I have a 2 in the denominator and a 6 in the numerator. So those reduce. And also I have a x squared in the bottom and an x cubed in the top. So the x squared in the bottom will reduce that x cubed down to x. The 2 in the bottom will reduce that 6 down to a 3. So what I'm left with in the top is 3 times x, which is 3x. And what I'm left in the bottom is 4 times 1, which is 4. So most of this stuff reduced out, leaving me with just 3x over 4. If you wanted to do, those things in multiple steps, you definitely could, especially if you have a hard time keeping track of what's left over. But that's what you should end up with when you factor and then reduce as much as possible. Number 11, I have a rational expression times a rational expression. The numerator of the fraction on the left is actually already factored. There's nothing I can really do to that at this point. But the denominator of the fraction on the right isn't. So I'm just going to think about factoring or reducing each part as much as possible. And what I can do to that fraction on the right is factor out a 4. And now I'm looking for things that reduce. So I have this y minus 3 binomial in the top and bottom. That reduces. And then I have a bunch of x's and y's kind of all over. So I want to be careful here. But I see I have a 5 in the denominator and a 15 in the numerator. So if I reduce those by 5, I get 1 and 3. I have x's in the bottom and top and y's in the bottom and top. So if I think about this, x squared in the denominator and the x cubed in the top, and then the y squared in the bottom and the y cubed. I'll do the y's first. Y squared in the bottom reduces with 2 y's in the top, leaving me with just 1. And then the x squared in the bottom reduces with the x cubed, leaving me with just 1x in the top. So now I've reduced everything. I want to see what's left. I'll highlight it in orange. So I have a 3 and an x and a 3 in the top. 3 times x times 3 is 9x. And in the bottom I have 1 times 4, which is 4. So my final answer here is 9x over 4. Number 12, I have 2 rational expressions being divided. So the first thing I like to do is change it to a multiplication problem. So keep the first fraction as is, and then times the reciprocal of the second fraction. So that's the first step I do. If you do that first, then we would handle it just like we did previous problems. Now I'm going to have to factor each part of each fraction as much as possible. So the numerator of the first fraction factors in x minus 4, x minus 1. You've got to be careful there. Factors of 4 that add to negative 5 are only 4 and negative 4 and negative 1. And then the bottom of that fraction, only a greatest common factor comes out. The top of the fraction on the right, I can factor out a 2x, and I get 2x times x plus 3, and the bottom factors in x minus 4, x plus 1. So right now I have 2 rational expressions completely factored. And what I'm going to do now is see what reduces. So I have an x plus 3 in the bottom and the top. That reduces. Cross it out. I have an x minus 4 in the bottom and the top. That reduces. Cross it out. And then I have 1x in the bottom and 1x in the top. Actually, those reduce as well. So what I'm left with is 2 times the quantity x minus 1 in the top and x plus 1 in the bottom. That's all that's left over after I've gone through all the reducing. So once you've turned it into a multiplication problem, we handle it just like we did previous ones, which is factor each part as much as possible and then see what reduces before you multiply them together. I'm going to do something similar for number 13. First, I'm going to factor 2 out of the first part, so 2 times the quantity x minus 3. The bottom factors into a difference of 2 squares, which is x plus 5, x minus 5. It's already multiplication, so I don't have to flip anything. The top factors into x plus 5, x plus 1, and the bottom factors into x plus 3, x minus 3. So that's everything factored as much as possible, and now I'm looking to reduce. So I have an x plus 5 in the top and bottom, that reduces, and an x minus 3 in the top and bottom, and that's actually it. So what I'm left with in the top is 2 times the quantity x plus 1, and what I'm left in the bottom is those 2 binomials, and I would leave them unmultiplied out, leave them exactly how they are. Multiplying them out doesn't make it any simpler. I think it actually makes it more difficult. And then number 14, I'm going to first change this into a multiplication problem, seeing that it's division. So rewrite it exactly how it was. Then I'm going to factor each part of each fraction as much as possible. So the top will factor in x plus 2, x plus 3. The bottom will factor into x minus 4, x plus 3, times the top will factor in x plus 5, x minus 4, and the denominator of that second fraction now doesn't factor at all. And now I'm going to look to see what reduces. So I have an x plus 2 in the top and bottom. That reduces, and I have an x minus 4 in the top and bottom. And then I also have an x plus 3 in the top and bottom. See, they don't have to be diagonal. One just has to be in the bottom of a fraction. One has to be in the top as long as the two fractions are multiplied. So all I'm left with is actually x plus 5, and that would be my final answer. And I'm going through the factoring stuff a little bit quickly. I'm hoping that as we're doing these, the factoring part isn't tripping us up as much anymore. But if you're curious on where I got my factors, I'm just going through and building my binomials the same way we did when we were solving quadratics and the same way we did when we were dealing with polynomials. So number 15, I notice it's already multiplication of 2 fractions, so I don't have to flip anything. So all I'm going to do is try and factor each part as much as possible. So p squared minus 18p plus 81 factors into p minus 9, p minus 9. And then the denominator of that first fraction, all I can take out is the greatest common factor, so p times p plus 3. The top of the second fraction is a difference of 2 squares, so it factors into p plus 2, p minus 2, and the bottom factors into p minus 9, p plus 2. So now I'm going to see what reduces. So I have a p minus 9 in the top and bottom, and a p plus 2 in the top and bottom. So all I'm left with in the top is those 2 binomials, p minus 9, p minus 2. Leave them unmultiplied. Multiplying them out doesn't make it any simpler. And then p times p plus 3 in the denominator. Because the 2 in the top are binomials, you can't cancel with any of the p's in the bottom. They're all individual factors, so keep them as individual factors. So the last problems that we have to deal with rational expressions is solving rational equations. So the idea is we have an equation that involves fractions. And the quickest way to solve these equations would be to find a number or an expression that when I multiply the whole equation by it, all the fractions cancel out or reduce. So what I'm essentially going to do is find what we call the least common denominator so that I can clear fractions in the equation first. So looking at number 16, the denominators are just numbers, 4 and 6. So when I'm looking for a common denominator, I'm basically looking for the smallest number that 4 and 6 can both go into. So the easiest way to do that is just to list the multiples of each number. So if I list factors of, or multiples of 4, 4, 8, 12, 16, 20, so on and so forth, list multiples of 6, 6, 12, 18, 24, so on and so forth, the first number they both have in common is 12. So that's what we call our least common denominator. So what I'm going to do now is take my least common denominator as a fraction, so whatever it is over 1, and multiply it by everything in the original equation. So here's how you'd write it. 12 over 1 times 3x over 4 equals 12 over 1 times 5 over 6. Notice, 12 over 1 is just the least common denominator as a fraction, and then I'm multiplying it by each part of my original equation. And here's why we do that. What you'll notice is I have 12 and a 4 a 12 in the top and a 4 in the bottom, those reduce. If I divide them both by 4, I'm left with 3 over 1. So then what I have is 3 times 3x in the top, and then 1 times 1 in the bottom, which is just 1, so I end up with 9x, no fraction. If you do this correctly and identify your least common denominator, what your result should be is an equation without fractions, if you did it correctly. And then in the on the right side, I have a 6 in the bottom and a 12 in the top. So if I reduce those to 1 and 2, what I end up with is 2 times 5 across the top, which is 10, 1 times 1 across the bottom, which is 1, so just 10. So 9x equals 10 is the equation. Divide both sides by 9, and I get 10 over 9, and that would be your answer. And if you wanted to check, if I took 10 over 9 and plugged it in for x, I should get a true equation. Both sides should be equal to each other. That's always a way you can check. So that's the process when it's just numerical denominators. Now if you look at number 17, we have a little bit more going on in the denominator. So what I like to do is think of 3x as really 3 times x. And then if I want to find my least common denominator, I essentially want to think about the different factors that appear in my denominator. So numerically, I have a 3 that appears in 2 different denominators, but it only appears at most 1 time in each denominator. So that means my least common denominator should have 1 3 in it. And then the other thing I have in a denominator is the factor x. So I have an x that appears once in 2 different denominators, but only appears once in each. So I need 1x in my least common denominator. So my least common denominator in this case would be 3x. That's the smallest denominator that all these 3 denominators can become. That's why it's called the least common denominator. Then what I'm going to do is take my least common denominator as a fraction and multiply it by every term in my original equation. So that's what I wrote there. You'll see 3x over 1 times the first term, 1 over 3x, minus 3x over 1 times 1 over x equals 3x over 1 times 2/3. Now, a bunch of stuff should reduce, leaving me with no fractions at all. So I have a 3x in the bottom and the top in this first fraction, leaving me with just 1 over 1, which is 1. Minus, please be careful, there's a minus there. The x's in the top and bottom will reduce, leaving me with 3 times 1 in the top and just 1 in the bottom, or just 3 times 1 is 3 over 1 is 3, equals, and the 3's will reduce, leaving me with just x times 2, which is 2x. So that's how this least common denominator clears all my fractions. Now what I have left should be an equation we can solve. So 1 minus 3 is negative 2, equal to 2x, divide both sides by 2. Negative 1 should be my x value that solves this equation. So that's the process for solving an equation. There's a few more examples obviously we're going to do that can be a little trickier, but once you know your least common denominator, we're going to follow the same process, which would be use it to clear fractions in our entire equation. So let's look at number 18. So what I'm going to do is find the least common denominator first. Notice I have 2 separate denominators. One is an x and one is an x plus 6. Those are 2 different factors, which means my least common denominator should have one of each of them, x times x plus 6. Be careful, a lot of people want to write x plus 6. When we're talking about a common denominator, we're essentially talking about factors, so they should be multiplied together. So now that I have my least common denominator, I have 1x and 1x plus 6, so my least common denominator has one of each. I'm going to take that as a fraction over 1 and multiply it by every term in my original equation. So feel free to pause the video so you can catch up to writing. If I'm ever going too fast, right, just pause it and make sure you're with me. That's just the least common denominator multiplied by every term. The reason why I do this is some stuff should reduce, right? So I have an x in the top of this left fraction and x in the bottom. Those reduce, leaving me with just 3 times the quantity x plus 6, all over 1, which is just 1. Equals, and then the x plus 6 part reduces, leaving me with just 2 times x, which is 2x. Now this is an equation that gives me the same solution as the first one, just without fractions. That's all I've done is cleared fractions. So I need to distribute, and then I'm going to solve for x. So I'm going to get my x's on the same side of the equation, so I'm going to subtract 2x from both sides, leaving me with just x plus 18 equals 0. If I subtract 18 from both sides, it would give me the x value negative 18, and that would be the solution to the equation. Number 19, first I want to find my least common denominator, so I like to think of, this is really 10, 5x, and 2. So if I look at just the numerical part, 10, 5, and 2, I need to think of the smallest number that they all could become. You might be able to see it right away and say 10, If not, just list multiples of each number. So 2, 4, 6, 8, 10, 12, so on and so forth. List multiples of 5, and list multiples of 10. And what you'll see is the smallest number they all share is 10. So my least common denominator has to have one 10 in it, and then one of my denominators has an x one time, so my least common denominator should also have an x in it. And then what I'm going to do is what I did before, multiply every term by 10x over 1, and that should clear all of my fractions. So here's me doing that. Just multiplying every term in the original equation by 10x over 1. And then I'm going to see what reduces. So I have a 10 and a 10 that reduces, leaving with just 3 times x. And then I have 10x in the top and 5x in the bottom. The x's both reduce, and then actually 10 and 5 reduce to 2 and 1. So then I just left with 2 times 1 in the top, which is 2. And then on the right side, the 2 will reduce the 5 down, or the 10 down to a 5, leaving with just 5x times 1, which is 5x. So here's my equation. Now I'm going to get my x's on the same side. You might want to move the 5x to the left. I think it's just easier to subtract 3x from both sides. It doesn't matter what side the variable's on. And then to solve for x, to divide both sides by 2. So I get negative 1 equals x, and there's my answer. You can always check, right? Put that number in the original equation and make sure that it works. Because it's possible that I got a number that doesn't actually work. All the ones so far have worked. We will come across one that we have a slight issue, and you'll see what I mean. But again, just take that number and plug it in for your variables in the original, and it should make the left side equal to the right side. So there's always a check there. Number 20, I see I have a y minus 6, and another y. So when I think about the least common denominator, I see that I have a y factor that appears once, at most once in each denominator, so I need one of them in my LCD. And then I have that y minus 6 binomial, so my least common denominator should be the quantity y minus 6 times y. So then what I'm going to do with that is multiply that as a fraction times every term in my original equation. Same process as before. The only thing that really differs is what your least common denominator is and how your fractions reduce. Now that I've written my least common denominator times every term, look to see what reduces. So I have a y in the bottom and a y in the top of that first product. So leaving with just 2 times y minus 6, all over 1, which I'm not going to write. And then minus, don't forget there's a minus there, so y minus 6 is reduced, leaving with just 3 times y, but it should be minus 3y. Sometimes we have a tendency to miss that minus there, call it a plus accidentally. And then equals, and then on the right side the y is reduced, leaving with just 1 times y minus 6, which is just y minus 6. And now again, all fractions are gone. This is something that should be solvable. This one has a distributing and some like terms to combine, but something we've solved before. So I'm going to distribute, leave everything else exactly the same, and then I see that I have like terms on the same side of the equation on the left, so I can take my 2y and negative 3y and add them, and I get negative y minus 12 equals y minus 6. And then I'm actually going to add y to both sides. You could subtract y from both sides, but I add y because it actually gets my y's positive on the right side. Then I'm going to add 6 to both sides, leaving me with 2y equal to negative 6, which gives me y is negative 3. So the solving of that one was a little bit more involved, but the clearing the fractions part was much the same as the previous problems. 21, first thing I'm going to do is make sure all denominators are simplified as much as possible. In this case, I'm going to rewrite it so that the x squared minus 4 is actually factored. So now, looking at my denominators, I have an x plus 2 that appears once in 2 different denominators, so my least common denominator should have one of them. Then I also have an x minus 2 that appears once in 2 different denominators, so my least common denominator should be both of those factors together. Now once I have that, I'm going to take that as a fraction and multiply it by every term in my original equation. So I'm just writing that here. In parentheses each factor, and then times each term in the original equation. So now I'm going to look to see what reduces. All fractions should clear at this point if my least common denominator is correct. So this x plus 2 and x plus 2 would reduce, leaving me with just x minus 2 equals, and then the denominator perfectly reduces with both factors in the numerator, leaving me with just 4. minus, and then the x minus 2 is reduced, leaving me with just 1 times the quantity x plus 2. And here's where that minus is really, really important. It's minus the quantity x plus 2. The easiest way, if you forget the parentheses, your value will be off for sure. So now that I have this equation, I'm going to first distribute that negative. So I have x minus 2 equals 4 minus x minus 2. And then I'm going to combine the like terms on the right side. And now I'm going to get my x's on the same side. The easiest way to do that is actually just to add x to both sides. Gets both x's on the left. And then I'm going to add 2 to both sides. 2x equals 4, which means x is going to be 2. So now, circling that is great, means that's my answer. But again, like I said before, you always want to kind of check, make sure that value makes sense. So if I were to plug that back into my original equation, I'll just show you that real quick. I'm just going to rewrite my original equation up here. Now if I were to plug 2 in for the variables, here's what I would get. 1 over 4, because it'd be 1 over 2 plus 2, which is 1 over 4, equals 4 over, and then 2 squared is 4, so that becomes 4 minus 4, minus 1 over 2 minus 2. So what happens is I get 1/4 equals 4 over 0 minus 1 over 0. The problem is anything over 0 doesn't exist, which means 2, although it worked for what we did, doesn't actually solve the original equation. Now that doesn't mean we made a mistake. All that means is when I multiplied to clear fractions, it created what we call an extra solution. So it doesn't actually work in the original, meaning that original equation has no solutions whatsoever. That happens at times. It's pretty rare, but it's always a good idea, to, especially with solving, to make sure that that value works in the original equation. And if it ever gives you something that's undefined, either you made a mistake or the equation has no solution in general. That is a possibility, especially for rational expressions. So this one actually has no solution. If you would have gotten all the way down to x equals 2, like you really understand the process, right? You just forgot to check. That's always a possibility. Just at least look at the denominators and see if what you got makes any of the denominators 0, because if it does, then that can't be included as a solution. And then the last problems here, we want to solve the equations the same way. So the first thing I'm going to do is first examine all the denominators. Minus 5 is not a fraction, so I'll make it one real quick. And then I'm going to find my least common denominator. And what I see is I have the factor x plus 2, and then the only other factor I have in the denominator is 1, so I don't need to write a 1 out front of that quantity. That is your least common denominator. So I'm going to multiply each term in that equation by the least common denominator. And once I've had that written, again, it's x plus 2 over 1 times each term. Some stuff should reduce. So the x plus 2 is reduced there, leaving with just 2x, minus, nothing reduced in that second one because 1 was the denominator, which is fine, which means I just have 5 times x plus 2 in the top, equals, and then the x plus 2 is reduced, leaving with just 7x. And now I'm just going to solve that as if I would any other equation. Distribute. Please make sure when you distribute that minus 5 that you multiply both terms by minus 5. We have a tendency to call that a plus 10, not a minus 10. It'll definitely affect your solutions. Then I'm going to combine those like terms on the same side, and then get my x's on the right side. The reason I got them on the right is because it makes them positive over there. And then let me back up a little bit on the solving here. So once I added 3x to both sides, I get negative 10 equals 10x, and then divide both sides by 10. So x is negative 1. And again, if I look real quick at the denominator, plugging negative 1 in any of the denominators doesn't make 0, so that's fine for a solution. That's essentially how quickly you need to check. Just plug it in the bottom. If it makes it undefined, then you can't include it. You probably have no solution. But again, like I said, it's rare. It only happens in special cases. First thing I'm going to do for 23 is factor each denominator as much as possible. If you try and examine the denominators unfactored, sometimes you won't create the smallest common denominator. You'll create a common denominator, but not the least common denominator. So then if I look at 23, I see I have an x minus 1 that appears once in every denominator, so I should have one of them in my least common denominator. But then I have 3 different numbers, 5, 2, and 4. So to find the number that they all can be, I essentially just want to list multiples of each number until I see one they have in common. So I'm just listing multiples of each number. And what you should get to is the fact that 20 is the smallest number they all can be, which means my least common denominator is 20 times x minus 1. So then I'm going to multiply each term in the original equation by that least common denominator over 1. So I'm just writing that here. And then again, a bunch of stuff should reduce, leaving me with just an equation without fractions. So let's go through the reducing. So I have the x minus 1 that reduces, and then 5 and 20 also reduce, leaving me with 4 and 1. So I just get 4 in the top times x in the top, which is 4x. And then the second one, there's a minus there, be careful. And then the x minus 1's reduce again, and the 20 and 2 reduce to 10, so I just left with 10 times the numerator, which was x minus 2, equals, and then the x minus 1's reduce, and 20 and 4 reduce to 5 and 1, so therefore I'm left with 5 times 5, which is 25. Now this equation is one that we've solved. You distribute the minus 10, combine your x terms on the same side, so negative 6x plus 20 equals 25. Subtract 20 from both sides. Negative 6x is 5. Dividing both sides by negative 6, I get negative 5 over 6. So that's solving rational expressions and simplifying rational equations. If you can, multiply rational expressions, divide them, and then solve equations, you should be in pretty good shape for this topic heading into the final exam.